Hi everyone, and welcome to another video of differential equations. So today I want to introduce another type of differential equations. So today we're going to be dealing with homogeneous differential equations. What are these and how do we work with them? Let's find out in today's video. Alright, so now that we're done with separable differential equations, we're now going to move to another type. So today it's homogeneous differential equations. So what are these? What I would basically call these are differential equations that are not necessarily separable when they are given to you, but they can actually be transformed into separable differential equations. So that means that by first look you'll actually see that they're not separable, but then when you work them out through a certain method, you can actually convert them into a separable differential equation before you actually work them out the way you do other separable differential equations. That's basically the definition. So homogeneous differential equation is one in which all the terms are of the same degree. So how are you going to know that a certain differential equation is actually homogeneous? So you're going to check for if all the terms are of the same degree, that is, all the terms are of the same dimensions. So what are these dimensions? Now let's take a look at this case. So this is the differential equation that we're looking at. So in case you want to know how to measure dimensions, this is how you do it. So now in this case the dimensions are L times L times L over L, which is equal to L squared plus L squared. So what happens is you look at each of the variables involved. So now when you see the variable of the variable x, that is actually a dimension L. The variable y is the dimension L. dy is the dimension L. dx is the dimension L. Then as you can see here, we have this x which is squared. So this variable, because it's squared, the dimension is now L squared. Then here also, because the dimension is y squared, because the variable is y squared, the dimension is also L squared. Alright, so now that you see that, you can actually see that this and this cancel, and then we should actually remain with the 1. And then right on the left hand side, L times L is L squared. So as you can see, the most important thing I want you to see is you can actually see that the dimensions on the left hand side are equal to the dimensions on the right hand side. We're not looking at the fact that you can sum these two and get 2L squared. No, we're just looking at the L's themselves, because here it's L squared, then the values on the right hand side are also L squared, each one individually. This actually means that the dimensions are equal. So now if you have such a case, this is actually a homogeneous differential equation. So let's look at another one. So this is case 2. We have x dy dx is equal to 2x plus y. So in this case the dimensions are, so where there is x you put L, where there is dy it's L, where there is dx it's L. But now we don't consider constants to be dimensions, so we're only going to be looking at the x value right here. So this x is going to be represented as L, and then the y is also going to be represented as L. So in this case you can see that this and this cancel, and then we should remain with L is equal to L plus L. So also in this case you can see that the dimensions on the left hand side are equal to the dimensions on the right hand side. And like I've said before, we're not looking at the sum of them, we're just looking at the individual L values, because here all L's are to the power 1, then on the right hand side all L's are also to the power 1. So that means that the dimensions are equal. So hence this is also homogeneous. Alright, so now that we know how to test the dimensions of any differential equation to check whether it's homogeneous, how do we solve these differential equations that are homogeneous? So they can be solved using an appropriate substitution. Y is equal to ux, where u is a function of x. Now as you can see here, if I choose to differentiate this, I'm actually going to use product rule. I'll get dy dx being equal to u plus x du dx. Now these two equations, equation 1 and equation 2, are going to be very useful every single time we want to convert a homogeneous differential equation into a separable one before we actually solve it the usual way that we are usually accustomed to. So this helps to transform the homogeneous non-separable differential equation into separable differential equation. At this stage, the method used to solve separable differential equations can now be adopted. Or so look at some examples. So this is going to be example number 1. So we're being told, using the substitution y is equal to ux, solve the differential equation x squared dy dx is equal to x squared plus xy plus y squared. Now because we've already been told to use the substitution y is equal to ux, so that means we've already been told by the person setting the question that this is already a homogeneous differential equation. But we can actually go ahead to test it to see and confirm. So what you can see here is, if you look at the dimensions on the left hand side, this is x squared, which shall actually be L squared. Then we have dy dx, which is L over L, being equal to, this is L squared, this is L times L, which is L squared, then this should also be L squared. So I can already say the dimensions are actually equal, because this L over L will cancel and remain with the 1. So I'll be left with L squared is equal to L squared plus L squared plus L squared. So this is actually a homogeneous differential equation. So let's solve this. So we're going to let y be equal to u x, and you know that when you differentiate this, we'll get dy dx being equal to u plus x du dx. So what's the next step? So this is what we're given. This is the differential equation we're given. So what we're going to do is, where there is dy dx, we're going to substitute that with this value here. So where there's dy dx, we shall put u plus x du dx, as you can see right there. Then where there is y on the right hand side, we're going to replace that with u x. So as you can see, where there is this y, we put there ux. Where there is this y squared, we also put ux, as you can see right there. So the next step is to open brackets. So as you can see here, x times ux shall actually be ux squared. Then here we square both of the individual variables, then we have u squared x squared. Alright, so the next step shall be to factorize out x squared on the right hand side. As you can see, I can actually factorize it out, and then this is what I will have. Then I can say that the x squared values cancel, and then I'll be left with u plus x du dx being equal to 1 plus u squared. So the next thing I can see is this u and this u can cancel. And then when I do that, I'll be left with x du dx being equal to 1 plus u squared. So at this point, I can now already say that now my differential equation is now separable, because I can actually say that now I can easily combine all the variables that have u together and those that have x together. So this is now separable. So now when I separate them, I'll have 1 over 1 plus u squared du being equal to 1 over x dx. So now at this moment, I can actually solve it the way I solve separable differential equations. So now integrating both sides, I will have integral of 1 over 1 plus u squared du being equal to integral of 1 over x dx. So from here, I can already say that this should actually give me tan inverse of u being equal to ln x plus c. But remember that from y is equal to ux, u is actually y over x. So we're going to substitute that back there. So therefore, we now have tan inverse of y over x is equal to ln x plus c. And that is the answer that we are looking for. Alright, let's look at example number 2. So being told to solve x squared dy dx is equal to xy plus y squared. So now in this case, we've also not been told whether this is separable or homogeneous or any other kind. Now the first case here is to first test. Every time you're given a differential equation and you're not told whether it's homogeneous or separable, you can actually test and see if it is separable first. But I can already see that this is actually not separable, because there's no way I can fully separate the x values from the y values. So in this case, I'm actually going to deal with it as a homogeneous. But let's first test that. So let's test the dimension. So this is L squared, this is L over L is equal to, this is L times L, which is L squared plus L squared. So I can already say this is actually homogeneous by testing the dimension. So what we're going to do is we're going to solve it the way we did the first number. We're going to let y be equal to ux, and then we know that dy dx should actually be u plus x du dx. Then given this differential equation, as you can see right there, wherever there is dy dx, we shall actually replace it with this, and then where there is the value of y, we shall place there ux, and this is what we end up having. So now when I open brackets here, when I multiply this x within, I'll have ux squared, and then here when I square both individual variables, I'll have u squared times x squared. So the next step I can see is I can factorize out x squared, and this is what I'll have. So I can now see that the x squared values cancel, and then what I will be left with u is u plus x du dx being equal to u plus u squared. So I can also see that this and this cancel, and I'll be left with x du dx being equal to u squared. So this is now separable. So next I can actually now collect all terms that actually have the u variable, and what I'll have is 1 over u squared du. Then collect also all the terms that actually have the x variable together, and I'll have 1 over x dx. So now that I've seen this, now I can actually introduce the integral. So I can integrate both sides. So looking at the left hand side, when I integrate that, I can actually first convert it to u to the power negative 2, and that's what I'll have. So on the left hand side, when I integrate that, I'll have negative u to the power negative 1 being equal to ln x plus c. So this is what I end up having, but that is the same as negative 1 over u being equal to ln x plus c. But from y is equal to ux, remember that u is actually equal to y over x. So therefore we now have negative x over y is equal to ln x plus c, and that is the answer. Alright, so question number 3, we're being told using the substitution y is equal to ux, where u is the function of x, to solve the differential equation x dy dx is equal to x plus 2y, given that y bracket 3 is equal to 1.5. So we're being told to solve this using the substitution y is equal to ux. Now, because they've said this, it actually means they've already identified it for you as being homogeneous. But I can still test the dimension. So this is L times L over L is equal to L plus L. And like I said, we don't consider the constant, so we shall only focus on the y. So this is L. So I can already say I'll end up having, so L over L cancel, and I'll have L is equal to L plus L. So this is actually homogeneous. So the next step is I'm going to solve it the normal way. So I want to let y be equal to ux. And remember, dy dx is now going to be equal to u plus x du dx. Now, given this differential equation, where there is dy dx, I'll actually replace it with that, and where there is y, I'll replace it with ux. So now I'll end up having this. So next I can see that I can factorize out x, and this is what I'll have. Next I can say this x and this x cancel, and I will be left with that. So next I can actually see that I can have this u value is combining, and then I have 2u minus u, which is actually u. So this is what I'm left with. So now at this point, this is now separable. So now I can separate all of them, and I'll have 1 over 1 plus u du is equal to 1 over x dx. So next I can integrate both sides this way, and then when I integrate the values on the left hand side, I'll have ln 1 plus u. Integrate the values on the right hand side, and I'll have ln x plus c. Now from y is equal to ux, I can get the value of u, which is equal to y over x. So therefore we now have ln 1 plus y over x is equal to ln x plus c. And then I can actually get the LCM right here, and I'll have ln x plus y over x is equal to ln x plus c, and that is the answer. Now, after we've done that, now the next step is we're given conditions in the question. Let's look at those conditions quickly. Now in the question we'll be told that given that y bracket 3 is equal to 1.5. Now this what this simply means is that 3 is actually representing the value of x, as you can see, and then it means that when x is 3, y shall actually be equal to 1.5. So that's what it simply means. So what that means is inside this equation here, where there is x, we're going to place a 3. So we're just going to substitute y is equal to 1.5 when x is 3. So this is what I'll end up having. Now right here, the left hand side, 3 plus 1.5 is 4.5. So I have 4.5 over 3, which is equal to ln 3 plus c. Now I can actually collect all the values that have ln together, because the goal is to find the value of c. So I have ln 4.5 over 3 minus ln 3. Now when you have natural logarithm subtracting, it's the same as division. Now I can change that division time to multiplication side and sign, and I'll have a third. Now right here, 3 times 3 is actually going to be equal to 9. So what I'll be left with is ln c is equal to ln 4.5 over 9, which is actually equal to a half. So I have ln a half. So c is actually ln a half. So now substituting for c back into equation 1, I'll have ln x plus y over x is equal to ln x plus, now where there is c, we are going to actually put ln a half, and that is the final answer. So question number 4, we're being told to solve x squared plus y squared, these are in bracket, times dy dx is equal to xy. So the first question is this actually homogeneous? So let's test that. So now we have, this is L squared plus L squared times L over L is equal to L times L, which is actually equal to L squared. So L over L cancel, and I'll be left with L squared plus L squared is equal to L squared. So this is actually homogeneous. So we can actually solve it the way we solve homogeneous differential equation. So we're going to let y be equal to ux, and then where there is, then we now to differentiate this, dy dx should actually be equal to u plus x du dx. So given this, where there is dy dx, we're actually going to place this, we're going to place this value right here, as you can see. Then where there is y, we're going to replace it with u, x, as you can see right there. So as you can see, when I open the brackets, this should actually be u squared x squared. Then when I multiply this in, I'll have ux squared. So next, I can actually see it from here. I can factorize out x squared, and this is what I'll have. So I can see x squared values cancel, and then this is what I'll be left with. Alright, so the next step is I can actually divide this on both sides, and this is what I'll end up having. So next, I can actually see that now everything is separable. I can actually now combine all the values of u together in this case. So I can have it this way. So I'll have x du dx being equal to u over 1 plus u squared minus u. So solve that and get the LCM, and I'll have u minus u into 1 plus u squared over 1 plus u squared. So this is what it will look like. So solve that further, open the brackets, and I'll have u minus u cubed over 1 plus u squared. So u minus u is actually 0, so I'll be left with negative u cubed over 1 plus u squared. So now I can actually now separate all of them, and I'll have 1 plus u squared over negative u cubed du is equal to 1 over x dx. So now everything has been separated. I can actually now separate these individually to actually make it easier to solve when I introduce the integral. And then I can take the negative outside to leave everything like that. So this is what I end up having. Now you can see that this and this reduce, and I'll be left with 1 over u. So now integrating both sides, this is what I'll have. Now there is this negative 1 outside the integral, so you actually have to remember that that's what we've done. Now 1 over u cubed can actually be changed to u to the power negative 3. So integrating that, I'll have negative outside into u to the power negative 2 over negative 2 plus ln u equals ln x plus c. Now I can rearrange this. This can actually be rearranged as negative 1 over 2u squared. Then if I bring that negative inside, I'll have 1 over 2u squared minus ln u is equal to ln x plus c. Now from y is equal to ux, I can actually get the value of u as y over x. So plug that back in, and therefore I'll now have 1 over 2 into y over x, then square that, minus ln y over x is equal to ln x plus c, and that is the answer that they wanted. Alright, so I have an exercise for you. It's an exercise of 6 numbers. I encourage you to try this out, and I believe that after you've done this, your knowledge will be perfected of homogeneous differential equations. The answers are right there in brackets in brown color for you to actually compare with what you get after solving. Thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. I hope the numbers were sufficient for you. If this video was of help to you, feel free to give the video a like, a thumbs up, and then feel free to share the video with all those that you can and help them out if the video really helped you. And then you can leave a comment down in the comment section for me, and I'll get time to reply to you. Thank you so much for watching. I'll see you in the next video.